Marcus blue. Marcus is so good. Okay. Mini camera. Okay, come. Let's start today. Okay, it's a bit late already. Okay. We're gonna try to achieve as many questions as possible today, lah. I can't speak for very long without talking. Okay, but anyways, let's just start about today. I want you guys to turn over to question 2 first. We start off with a recap question. Later we need to try others. Okay, we try to go as fast as possible. Okay, try question 2, part 1 first. Okay, this one is a mechanism question which we've done for the past 2 lessons. Okay, give it a try first. Okay, I'll need time minutes. Okay, give you guys about 3 minutes. Okay, 3 minutes to try this. Describe means all the arrows and stuff. So remember for this topic, what's the reaction called? Yes, okay, so we need to describe that. It's basically the arrow movement plus we need to write the title also. Yeah, okay, just follow your reach attack info. Forget a bit, at least you can rely on the effect. Yeah, those arrows. Okay, you need this. Yeah. I don't know, power. Yeah, move on back to it. Describe means no. Yeah, I know they always like to use the word describe. Describe doesn't mean in words, no. Yeah. Okay, if you're done, you can just move on to part B. When time's up, then I'll go over the part yes. You want you extra. So we started off like the study of one takes proper. Arrow down for it was not
Okay.
so put the eight and the
Oh, you have oh. Okay, oh, yeah, terrible, right? Oh,
second,
yeah.
but I don't know. Okay, gonna write down the answer. Okay. Okay, just gonna use this as a recap. Later we might find more of the same question. Okay, so always note a few things. Okay, I didn't read. Okay, go and check your slow step and fast step also. First step is slow because there's a lot of braking going on. Okay, your reach must affect the poor, and you must also tell me why H is poor. Okay, by giving me your partial charges. Okay, your arrow from here going towards BR also. Okay, so here bromine gains an electron, and by gaining an electron, you must have a negative charge. Okay, so that becomes reach. That guy there is a nucleophile. Okay, then from here, also go and check your positive charge to go here. Because we have two carbons, and the positive charge should be the more stable version, which is on the secondary carbon cation. If you put a positive charge here, means the first carbon has the H. You want to draw the H, go ahead. Okay, but it's invisible. Okay, so don't need to draw the H. All good? Okay, then from there, you can take out the thing again. Okay, just make sure I know this. Okay, this part is good. Okay, you guys have drawn your lone pair and then the arrow pointing towards the carbon. Now remember, don't point towards the positive charge. Okay, avoid any ambiguity. Okay, from there, very simply, this is your first step, and that's your final answer. This is the major product. You want to draw your H there also can. Okay, but let's keep it consistent or no interest, keep visible. Okay? Okay, then from there, just go over the part B. Okay, do part B and part C together. Okay, they're quite similar. I thought you got two products. Oh, okay. Okay. There's no, okay, for those at part 3, there's no symmetry, right? In fact, is there a chiral center? Check why. Yeah, okay, this is a chiral center. It should rotate plane polarized light, but they say it doesn't. Why? Yeah, that's all. There's only one answer. Okay, you have an equal proportion. Yes. Equal proportions of two enantiomers. No, cis trans. Cis trans is cis trans. Enantiomer is enantiomer, separate. Yeah, okay, so it's enantiomers, two enantiomers. Okay, they are in equal proportions in the same mixture. But isn't that just one? Or is that two? Can you remember how the racing mixture was formed? Okay, can you just look at this carbon here? This carbon here is there's a very special shape around this carbon that allows it to be attacked from both sides. Trigonal planar, yes. Okay, this particular carbon, the rest are not. This carbon here is trigonal planar because it's flat on this carbon, right? The lone pair can attack from the top and the bottom with equal chances. And because of that, that's why you actually form two of these products. It's not shown in your mechanism. You're not supposed to show it in your mechanism. But you just need to acknowledge, right, that you do form a racemic mixture from it. Okay? How the racemic mixture forms. Yeah, because of that, then yeah,
Yeah. Yeah,
no, Oh my god. Drink more water. Drink more water. I don't need to like after future that time sick also. Yeah, like that. It's more than that, right? Oh, your life very 精彩. That's correct. You can phrase it as electron donating account. Okay, come, let's go over the answer, part 2 and 3. Okay, so they're asking for 2 bromobutane versus 1 bromobutane. Okay, you can already see, right? Okay, it's definitely possible for the PR to be either here or the first position, right? Okay, but why doesn't that happen? Okay, there are only 3 points over here. Okay, what's the first point? What do you compare first? Okay, first you talk about the number of.
Electron donating out.
Yes, okay, you need the whole thing. Okay, first you tell me the secondary carbocation. Okay, remember, I'm mostly focused on the carbocation ion's stability. So I talk about the carbocation ion having more electron donating alkyl groups than the primary one. Okay. Okay, then afterwards then. Yeah, okay, the positive charge will be correct. Okay, so remember, when you give the positive charge means the carbon is poor. Okay, but the electron donating alkyl groups will make it less poor. But it's just that having more groups will make it even less poor, right? Okay, so the positive charge of the secondary carbocation is dispersed, but to a greater extent. Okay, then from there, you have to link it to the final one, stability. Okay, having a smaller positive charge, the charge smaller, a little bit more stable, not so reactive, right? Okay, so secondary carbocation is more stable. Okay, because of that, right, your 2-bromobutane is more likely to be formed. You want to add that in also can. Okay, so more stable and more likely to form. Just be mindful of the keywords lah. Okay, you go and remember the keywords, right? Then after that, you won't be as lost with this question next time. Okay, 3 keywords. Yeah, then that's pretty much it. Okay, how about the part 3, part C? Okay, so this kind of question, right? Okay, it's always pointing to one idea. You can write it down also, it's race mixture lah. Right, okay, you can see that this compound, the product, is chiral, but yet it's the overall product mixture is not. Okay, because you have 2 enantiomers actually formed from this mechanism. Okay, for the explanation, right? Okay, I just need you all to first take note. Okay, part 1, you must tell me it is trigonal planar. It all starts off with that. Okay, and because it's trigonal planar, then the nucleophile, okay, you can call that a nucleophile. I in this case use PR minus. Okay, then from there, just tell me can attack the carbon with the positive charge from both sides of the plane. Okay, with equal probability. Okay, and then you can just end it off forming a racemic mixture. And remember, our racemic mixtures, are they optically active? No, okay, not optically active, they cannot rotate because both of the enantiomers will cancel out the rotation. Okay, this kind of question, they can only test the phrasing. So it's just this. Okay, but a lot of people tend to forget this first part and they just ramble on with the second point. But again, that one cannot give you the marks. Because everything in order to get this 1 mark. Okay, it's not difficult to get this 1 mark because it's the same whole explanation. Okay, can? So that's that.
What do you mean by the carbon?
The shape of the carbon here in particular is trigonal planar. I'm not referring to the whole intermediate as trigonal planar. I'm referring to this carbon here. Or you can say, to be more specific, you can say carbon with a positive charge is trigonal planar. That's what I'm referring to. Okay, there's a H missing. Okay, you realize, okay, this guy has a H originally, but then he just broke the double bond for and got nothing in return. So he still had now he has only 3 bonds, that's why it's a positive charge. Okay, I know it's a bit you're not very used to seeing skeletal formula yet. Okay, but don't always just assume you see 2 bonds means there's only 2 bonds. Always ask yourself, is there a hidden hydrogen? Or are there any hidden hydrogens? Okay, then you'll be more careful. I know now you're not very used to it yet. Okay, so it's a very basic question. We're going to start to wrap it up also. Okay, once you're done, can you look at question 4? Okay, we're going to deal with different types of questions, and until the end of today, we're going to deal with something a bit more advanced. Okay, for the elucidation questions. Okay, so question 4, we'll be discussing this thing called reaction synthesis. Okay, I'll do like one question with you guys, then the rest we can let you guys try also. Okay, I'll just finish copying first. Fighting the urge of call. Okay, so we'll turn over the question 4. Okay, come, let's take a look. Okay, any questions so far? Yeah. So for question 4, right, reaction synthesis is basically you are trying to construct a new item from an existing reagent. Okay, you're just trying to convert and transform one thing to another. Okay, so if you look at the first question here, 1 chloropropane turned into 2 chloropropane. Okay, of course, these kind of things never happen in one step. They happen in a series of steps. Okay, and you need to be well versed enough with your mechanics, with your reactions. So I hope you all have the notes with you also. Okay, but I'll do a summary with you guys. But let's look at this first question. We want 1 chloropropane, so we draw 3 carbons, put a C down on the first. And then we somehow need to turn this guy. Don't know how many steps it takes, so just leave a bit of space. Okay, then you must get 2 chloropropane. That's your final product. In the meantime, we need to exhibit a few reactions. Okay, but I know you all forget the reactions really. So I need you all to focus on one thing. I know each reaction has a reagent and condition, but that one I don't expect you guys to remember now off the bat. Okay, it's good to start picking it up, okay, but don't need to like purely memorize by now. Okay, but remember, let's list down all the possible reactions we learned in this topic. Okay, as we go higher level, we learn more topics, right? You can't do this. Okay, it should be your head. Okay, so what are some reactions? Alkenes. Let's start with anything. Free radical, no, that's for alkanes. Okay, alkanes undergo substitution because they are saturated, but this is a double bond, unsaturated. Right, okay, this topic is on alkenes. So alkenes can undergo what reactions? Okay, good. We start with electrophilic addition first. But under electrophilic addition, right, we got a few reagents. Okay, so let's list down everything. To draw the mechanism, right, there are 3. Okay, any reagents that we use to undergo electroadd? Okay, we got HBr, HCl, whatever, so I call them HX. Okay, anymore? Okay, X2. This one is in the elemental state, so it's either liquid or gaseous state. But there's also X2 in the equal state. This one is the mechanism a bit funky towards that. Okay, but there's also other electrophilic addition reactions. Okay, the first one is with water. Now, this one I don't need to draw mechanism. Okay, you just need to know how the reaction looks like. Okay, just a quick recap. If you take an alkene, you react with your water. Your water is pretty much just like H and OH. So you can see the pattern as to how the product is formed. The H is added here, the OH is added here. So you can see how water is being added. You don't need to know the mechanism for this. Just know how it's added can be. Okay, there's another one, remember. Okay, it's not oxidation yet, okay, because it's still under electrophilic addition. We add hydrogen gas. And guys, there's another name for this reaction. When you add hydrogen gas to anything. As hydration, no, close enough. Hydrogenation, okay, but there's a more legit term for it. Reduction, yes. Yes. That's exactly, and then you add oxygen, it will be oxidation instead of. Yeah, okay, so you can add your H2 gas. Okay, and do you remember what it forms when you add hydrogen gas?
Okay.
Yes, okay, you form an alkane. You're just adding H's so it becomes saturated. Okay, can? Okay, so next, right? Outside of electrophilic addition, what else do we have? Okay, we have elimination also. Now remember, elimination is what you're getting rid of. Good. Okay, I only need you all to bear this in mind because second part B, okay, will test you on this. You can only get rid of HX. Okay, let's move on to the third one. What's the third reaction? Okay, oxidation, but we have classified it into 2 aspects, right? What are the 2 types of oxidation? Okay, partial, okay, mild oxidation. Oh no. Okay, yes, mild and okay, we don't really use the word strong oxidation. You can use it if you want. Okay, but because we are trying to, what's cleavage mean? What does cleave mean? Cut. Yeah, okay, you want to cut and break down bonds. Okay, that's what cleavage means. Okay. Okay, so yeah, okay, that's all the reactions that we had. What's the difference in conditions between mild and strong?
Low, cold.
Low. Yeah, okay, cold and heat. Okay, so just remember the difference. The reagents are all the same because of oxidizing agent. Now, with that said and done, okay, I'll go through part A with you guys. Okay, because let me show you guys what the logic is to start with this question. Some of you guys see this, you just don't know where to start. So I just whack one random thing up. In fact, I can't even refer to this, right? Because am I starting with alkene? No, not. Okay, but what can I do? Here, I want to change the position of Cl from the first to the second. Have I learned a reaction where you can just like magically shift the thing? Not directly, okay, that's why there's a few steps. Okay, any suggestions? Okay, addition is only if there's an alkene, but I don't even have an alkene to start off with. Okay, then why not? Okay, see right, yeah, okay, we are starting the thing already. One of y'all said alkene, but we don't have alkene, so we make an alkene. No? Okay, so if you want to make an alkene, what can we do? I must start from here. How do I go from here, right? I don't go to the end yet, but how do I go to an alkene first? We reduce. Nope, that's not the correct reaction. But the idea is there. Elimination. Good. Can you remember? Elimination is just the opposite of what? Exactly. Addition, you're trying to make a reaction from what to what? A compound from what to what? Okay, basically an alkene to a L doesn't have to be an alkene, but alkene is basically unsaturated, right? So it becomes saturated. There are many types of saturated compounds, as you can see. This is considered saturated also, but it's not an alkane, right? Okay, so let's be a bit more general here. Unsaturated to saturated, meaning to say elimination is yeah, the opposite, right? Okay, now you can form that double bond. Okay, so why don't we do that for this first? Okay, go and draw in the next product. Okay. Sometimes we multiply, okay, we have this first compound, then multiply something first. Okay, yeah, you want to form an alkene, go ahead now. Okay, so what's my compound first? Right. Okay, don't need to tell me all the reagents and conditions here. Okay, again, they want you write down, you can write down first, but I'm more interested in the conditions. Okay, but anyways, okay, you are getting rid of a Cl and a H. HCl, okay, the H is come from where? I know the Cl is from here. Okay, does the H come from the same carbon? Never, again, never happens. Must be this side. Okay, so you remove the H here. I don't draw, I start to not draw already. No must get used to see. Okay, remove the H and the Cl. Okay, then you can form your alkene here. Okay, I'm not interested in the HCl, I'm only interested in the organic product. Okay, again, I don't know whether this is the only step. Okay, we need to investigate. Once we've gotten here, can we take the alkene and turn it into that? Can we do it in just one step? Can. Okay, that's the answer. Okay, yeah, how? How do I turn an alkene into a saturated compound? Yeah, in addition. What do you add here? Cl2, but I only see one Cl left. Because we have Cl. Okay, Cl, yeah, that's what I'm doing here. Basically, what I'm doing here is I'm just removing it and adding it back again. But you notice, how come if I remove and I add it back again, why don't I just get the original compound? How come I get that instead? Why do I get this compound instead of the original compound? Okay, question, guys. Because this is the major product. Good. Can you see, right? This is the more likely product to form compared to this. It's the question, the exact same question that we did just now. This is more likely to form because it's a secondary carbocation. This one is a primary carbocation. So that's the answer for this first question. Okay, for the elimination, yeah, suggest okay. For this kind of questions, they mark two things. They mark the reagents and conditions, and the intermediates, everything in between. Okay, so it's 3 marks because 1, 3. But I want you guys to write down, because for practice, I want you all to write down the name of the reaction. So this one in red, it's not required. Electrophilic addition. This one here is elimination. Again, not necessary, but just write down. Okay. Remember, elimination is ethanolic NaOH and heat. Just remember this for life. Okay. Yeah, elimination is just like that and forever. And ethanolic NaOH. That's the recipe. Never change the recipe. Okay, so that's it for the first one. Okay, so that's reaction synthesis. Okay, we can try part 3 now. Okay, this one I'll give you guys a bit of time to try. Cannot get, never mind, right? Okay, for part B, again, draw the starting and final compound first. Don't just draw one, then you don't know what you are trying to lead towards. Yes, again, two carbons, two carbons. Just an E. Does it matter? Does it matter where you put the chlorine? Ethene is okay, this one not nickel minor. It doesn't matter where you put the chlorine. Okay, two carbons. Doesn't matter where you put chlorine, it's metal. Yeah, okay, just follow what they say. If they never number the position means it doesn't matter. You all see this tip. If they never number the chlorine's position, that means it doesn't matter. But if they do, that means it matters whenever you want to do. You have to try and error. I don't want you all to just stare at the thing blankly. That one cannot, nothing will happen. I give you all the reactions here. Use pencil and try draw something. Must experiment. Okay. Okay. Along the way, I'll give you guys more tips for different types of patterns. This skill next topic and the following topic we use more. Now we limited. Try doing something to this guy. Just do something to this guy. I don't know. Try first. I give you guys 1 more minute to do that. When you don't discuss, don't just discuss and don't try anything out. Go and write something out. Must try out. Okay, no use just discussing. Okay, let's go through. Let's go through. Then a correct answer has emerged. Yes, someone has mentioned the correct answer. Okay, anyone want to try? Sarah want to try?
Yeah, sorry.
You want to answer? What do you think? Okay, but your logic just now was correct. Okay, what was the logic first? Okay, good. So you add Cl2 first. Okay, you're gonna add two Cls, one right on the double bond. So I look like this. Okay, now hold on. Your draw and time must be careful. Go and check that you still have two carbons. I still have two carbons, 1, 2. It's just one Cl just sprout out of it only. Can? Okay, then do it. Yes, exactly. Okay, so this question a little bit tricky. I add 2, but I remove only 1. Why am I able to remove only 1? Because I just now highlighted this. You can only remove HX. You'll never learn a reaction where you remove 2 Cl at the same time. Never. Okay, so you remove HX so that now I form a double bond, but 1 Cl is still stuck there. Yes, this one. Okay, then write down the name of the reactions and all the ingredients and whatnot. Okay, so again, I have an elimination on the second step. First step, I still have another electrophilic addition. Okay, good. Okay, ethanolate NaOH. The more you write this, the more you start to memorize. Okay, now Cl2 gas is added at room temperature. If you don't write room temperature, it's fine. You just leave it there. You're scared, you want to write, go ahead. Yes, correct. Of course, the one I talked about just now, we add water. Yeah. Okay, my bad. Butane 1-all, okay, we draw together lah. Then I let you all try. Okay, butane 1-all means OH. It is for the fourth 1, 2, 3, 4, and OH. Remember, because now you all just started drawing skeletal, right? Draw already, go and check, count the number of carbons. Make it a recurring habit. Okay, from there, we need to slowly get our, what's this? What's propanoic acid? What's oic acid? Okay, what's oic acid? It's just what functional group? Yes, COH, okay, carboxylic acid. We also went through this. Okay, but it's for propanoic. Propan means how many carbons? Three carbons. Okay, so always draw your 3 carbons first. 1, 2, 3. Then you add in the functional group. It's here. Okay, how is the functional group again? Okay, there's a double bond O, OH. Yeah, okay, so this is how the carboxylic acid functional group looks like. Okay, it's always on the first carbon or the last carbon. Okay, and this is when I will need you guys to write down a bit of a tip. Okay, because this one not very useful in this topic yet. Okay, but more useful for the next few topics. Okay, anyways, at the top of this page, write this down at the top. Okay, so serve as a reminder. For this kind of reaction synthesis questions, I want you guys to always count the number of carbon atoms. This is super ultra important because if there is a different number of carbon atoms, right, you can make your life a lot easier for this kind of question. For the past 2 questions, I'm not changing the carbons. I have 3 here, I end up with 3. I have 2 here, I end up with 2. That's why I never mentioned yet. But here, guys, let's count the number of carbons. Can you tell me something that you already have? Count meaning the start and the end. Okay, this is the first thing. Okay, it lost 1 carbon, right? From 4 carbons, somehow I can cut the number of carbons by 1. And you look at the list of reactions that we have learned. Is there any reaction here that can possibly reduce carbons? Okay, look a bit more carefully. There is 1 reaction here that can reduce the number of carbon atoms in the molecule. Your favorite reaction? Huh? Which one? Yes, your favorite reaction, right? Because you can actually cut the bonds. Hey guys, when you cut the bonds, you get smaller things, right? You cut something, you get smaller 2 fragments. Same idea over here. Okay, can mal-oxidation cut and you cut the number of carbons? What is mal-oxidation again? What are you cutting actually? Is it the whole double bond? You are just cutting the weaker bond in the double bond, right? Which is the what? What bond? Pi bond, exactly. Okay, then you add the 2 OHs there. Okay, so remember, guys, this reaction in this topic is known as step-down reaction. A step-down reaction, very important, not so much now, but in the future topics you will see. There's also step-up reactions, we'll learn that soon. Okay, a step-down reaction is something that can reduce the number of carbon atoms by 1. Okay, but I wouldn't say just by 1, it can reduce by any number, but in this case, it's just by 1. Okay, when you identify such reactions, okay, it makes your life easier because you are narrowing down to a certain set of reactions. Okay, but for this question here, for this topic, what we've done so far, oxidative cleavage is a step-down reaction. Because inevitably, you're cutting something, smaller pieces. Okay, this, yeah. Okay, so that means oxidative cleavage must happen somewhere. Now I'll leave it to you guys. I just tell you first, this must happen somewhere here. I don't know when, you're going to figure it out. Okay? Oh, perhaps I think, okay, we are. Okay, there is 1 reaction that you all haven't really learned yet. Okay, but so I want you all to modify this a bit. Okay, this OH, change this to Br first. Change the pencil or something, or whatever. Okay, the OH one you all haven't really learned yet. Okay, so you can change this to Br first. Okay, then try. Okay, try with the intention that you must make this happen somehow. Okay. Yeah, just change it to Br instead. You can still get that. Yeah, remember, oxidative cleavage is only for alkenes. I currently don't have an alkene. I remember the rule of oxidative cleavage. The rules, the first rule is to, okay, after you cut already, right, the double bond must do what? Okay, you add O to the double bond. And what's the second thing to check? Okay, if there's any H, then just add O to it. Okay, so if there's any H, okay, turn it into OH. You're just adding O's, that's what you're doing. It's the cut, hold the cutting.
We right there,
You don't need to draw the squiggly line. Squiggly line is for your own visual help. Yeah. You'll draw inside pen also, just don't make it like yeah, okay, so come, let's go over this. Okay, why this step down reaction thing is significant? It's because it tells you oxidative cleavage must happen. If not, you're gonna stare at this right for the next 50 minutes and nothing's gonna come to your head. Okay, oxidative cleavage must happen. And oxidative cleavage is only for alkenes. I don't have an alkene. How do I make an alkene? That's my first question. Elimination, good. Okay, why I told you guys to change this? Okay, OH also can undergo elimination one. But I told you guys elimination is minus HX. There's another one where you can get rid of water. We call that dehydration, but you haven't learned yet. Okay, that's why I changed it to PR first. Okay, not to worry. Okay, so we have the double one here only. All good with that? So the first position. Okay, then now should I perform my oxidative cleavage? Okay, can okay, we try. Okay, so remember we have these two carbons here, A and B. I usually draw the squiggly line, but honestly it doesn't matter. Okay, you cut A already, then what will happen? Can you get that? Okay, you can see that. Can what happened to B? By the way? Carbon dioxide. Good. Okay, why? What's this alkene called? I told you guys. Very easy way, very surefire way, right? Okay, to identify carbon dioxide is formed. We call this a what alkene. Yes. Okay, good. This alkene, I want you all to know it now also. It's called terminal alkene. What that means is that you will definitely form carbon dioxide. Okay, try to spot this. Is that important? It's an N. If it's in the middle here, that's obviously not an N. This one's an N also. Okay, the idea is this one very important deduction. Okay, if you see carbon dioxide produced, that means you know that the guy has a terminal alkene, something like that. Okay, all good with this. Okay, so reaction synthesis give you guys a bit of a sneak peek. It starts to get more and more as we go on. Okay, any questions so far? If don't have, okay, you still need to keep going up. Okay, I want to look at question 5. Okay, let's do distinguishing tests. Okay, I want you all to look at 5B. We don't care about A. A a bit boring. Okay, look at 5B. Okay, I want to show you guys the format of answering distinguishing tests first. Okay, then we work it out together. Okay, distinguishing test means imagine these two things in two separate test tubes. And in these two test tubes, you want to add something such that only one of the test tubes got some reaction, the other one don't have. And that's how you know something has different reactant now. Right? Okay, so for 5B, they are asking us to distinguish between two things and preferably draw it out. But this is the format. First, we can write down the reagents and pollutants somewhere up here. That's what we need to figure out. Okay, second one is build 1 in. So this build 1 in. Third one is, second compound is build 2 in. Okay, we do this first. And yeah, you all need to choose one reaction that has a special observation for only one of them. Okay, this one I'll give you guys a bit of time to think. Okay, remember my list is still here. I'm going to use the list. Okay, as the lesson proceeds, I'm going to remove this list. Okay. So best is if you write it down somewhere or you start getting in your head. Okay. Yeah, there are just two little test tubes there. If you want, possible, definitely possible. Your test for color change also can. Yeah. Your test for gas also good. Okay, I talk a little bit more. Guys, when you want to distinguish anything, you must distinguish number one, their functional group first. Functional group is the number one thing you see, but is it different functional groups? No, so slightly more tricky. They both share the same reaction base over here, but somehow they react differently. Okay. Okay, so I'm sure you got the answer. What do we do? What we do? Yeah, okay, that's the answer. Why? You look at these two guys, what's one special thing you spot? Yeah, okay, terminal alkene. This guy will only carbon outside. This guy doesn't. Finish. That's the answer. Okay, because I keep highlighting terminal alkenes. Right? KMNO4, H2SO4, and P. This is the same old package. Okay, just use it. Okay, what's the observations? We do this guy first, the guy at the terminal alkene. Okay, there's carbon dioxide. Okay, but before that, something else must happen. Okay, purple KMNO4 decolorizes, and then effervescence of CO2. Okay, now you don't need to say what bubble into lime water, that one is only for practical thing, right? Okay, here don't care, doesn't matter. Okay, brown PPT of MnO2 is if you write NaOH instead of H2SO4. Okay, the last time I went through this, I told you guys try not to write NaOH because you end up having to write another observation. Just use H2SO4, your life will be easier. Okay, so effervescence of carbon dioxide gas. And for the other one, right, don't just write nothing. Okay, the one apparently they don't accept. Okay, does purple KMNO4 decolorize? Yes, it does, guys. Okay, take note, it still oxidizes. It's just that there's no carbon dioxide gas. Be very careful here. You have an alkene, you get oxidized. So it will decolorize. Yes, as long as you decolor, if it decolorizes, that means the oxidation did proceed. Yeah. Okay, so just tell me no effervescence of CO2 then. Okay, moving on to part C. Okay, give it a try. Draw the structure first. Hexagon. Oh shit, okay. There's no R here. I think last time I also got it wrong. Slowly draw that one. We learn how to draw compounds. Okay, put it in this here. Speaking of spelling, I keep watching the stupid spelling program. All those little kids, right? Like, spell, wait, no, what? Shit, there is like spell something. Then can I have the origin? I think there's one called or there's one the stupid meme, spell negus. The kid like can I have the origin please? Let's say something. Can I be in a sentence please? Can I fool the parent, please? I don't know you can ask anything. Then you actually spell correctly, then you the very obvious sign of it. Wow, that's funny. Niggas. That's not swear, guys. Then I can spell when people don't watch it on. How do you spell the Oh, not harder than chemistry. Yeah. How do you spell? Wait, I'm gonna try. Alright, hey, hold on. What? Oh, wait. I got it. I got it. Okay. Wow. Yeah. There's a lot. There could be a whole that there's all versions. What? Yeah. This is the first try. What do you mean? I spelled it. This is the first thing that comes to my head. I know some people spell without the word. It's not too hard already. Two double. I eat two double. Wait. Wow, I do like buy express speed. Express speed. It works. I watched it yesterday. That's how we go for them. I didn't know you watch football. I think one back. Like, oh shit, go England. Go England. Ah, yeah, it doesn't matter. You can twist the thing however you want to place it however you want. Just make sure that the double bonds are on the first and the third position. Yeah, okay. First and the third, so you can just draw the same as before. Then the third one, just draw it like on the third bond. Yeah. Okay, let's give it a try.
Oh.
Okay, or you can just tell me the answer, just like shout answer.
Most of the shipping cases are 2 ins.
Okay, there's 2 bromines, okay, 2 moles. Could be. Okay, but you must have a different observation. I don't care if they have the same reaction, but if they have different observation, okay, can. You see that the previous question here, they have the same reaction but different observation. That's all that matters. Yeah, okay, so it doesn't necessarily have to be a different reaction. Okay, like if you say 2 moles of Br, 2 moles of Br, yes, it's a slightly different reaction, but you don't see something different because just because there's 2 moles. Yeah, you don't see anything different. Cannot see it. What do you mean? No, okay, whenever you do electrophilic addition, you will do for both. It doesn't discriminate, you just whack at the same time. It doesn't matter. Okay, but guys, I remember telling you guys there's a very special part of oxidative cleavage, and it has to do with this little pattern over here. Double bond, single bond, then double bond. When you have a double bond, single bond followed by double bond, there's a very special type of oxidation. Yes, basically that. What? Remember? But that thing will turn into what? Carbon dioxide water, which is effervescence law. Guys, go and refer to the notes. We drew the products for this exact food. Okay, we drew the product for this exact. Okay, go and refer to the notes. Okay, from there, go to draw the products again. I want you to just write down this one thing. There's a shortcut. Always spot the double, single, double pattern. And when you see this, quite likely, I wouldn't say it's 100%, sometimes it doesn't work. quite likely you will get carbon dioxide. Okay, so observations wise, same as above law. Yeah, okay, just know which one has the carbon dioxide. Yes.
So plain reagent.
Exactly.
Wait, the below one has the concept.
Yeah. Because I'll just repeat again. Okay, they have a double, single, double pattern. And remember, this guy here, we went through last lesson, it will create this thing here, which is your ethane dioic acid. Basically, both carbons are carboxylic acids. This guy will never appear because he will just turn straight to carbon dioxide. And this will give you your effervescence. Okay, let's try one more question before I take a break. Let's try question 7.
I play volleyball, right? I get my finger and it hurts.
Oh, normal now. No, never mind, it's normal after a while. Last time I jammed my finger, I jammed my nose, I jammed my. You just hit very hard and like, whoa. Okay, that time I play floorball, right? Then I stopped too early. And because like my school like that, right? Then the toes like here, then it hit them hard. Then I was like, oh shit, damn pain, take out my foot, right? Then it bruised immediately. Then a few days later, the toenail came out. No, but when it came out, it's not pain lah. It's just the initial jam, wow, damn painful. Yeah, but it was quite fun though. The toenail come out. Then like slowly come out. Then I keep taking pictures. And my friend last time was Snapchat, right? Yeah. Then I take really send my friend. Then he's like, why? I'm eating. I think I got photos too. Therapy. Oh shit, there's therapy in this. Didn't realize. Okay, let me help you guys out a little bit. Okay, you realize that yeah, it's just one reaction, of course, this oxidative cleavage. You are just except you are trying to piece the stuff back together. How on earth do you do that, right? Okay, so come.
Oh, just
Now, guys, the thing that can help you guys is numbers. Okay, so I want you all to draw these two guys out first. Hey, guys, when you do oxidative cleavage, what are the 2 steps that I told you guys? First thing, you turn your double bond into your O's, then turn your H into OH. And just reverse that shit, right? Okay, so what we're doing now is, what's the first thing we can do if we reverse the steps? Okay, turn the OH back into a H. Yeah, let's do that first. Any OHs you see here, yeah, let's turn it back to H. In other words, H is invisible, just delete the whole thing. Okay, turn the OH, I found another one, just delete the whole thing, but there's a H there, just keep it. Okay. Then after that, anything else we need to do? Remove the O on the double bond, right? I'm just reversing the process. Right? Okay, remove the O on the double bond now. So these are the parts we are trying to draw it together. Okay, now if you have an iPad, very simple, just go and just turn it around, right? Very simple. Okay, but we don't have that shit. Okay, so how? Numbers. Okay, keep in mind numbers. I want you to number whatever you want, but just keep it consistent. 1, 2, 3, 4. Okay, we have 4 carbons here. Okay, don't go and number these. These are like the broken portions, not a carbon. Okay, they are broken portions. Let me draw the squiggly line to show. They're not carbons. And then here we got 5, we got 6, we got 7, call this 8, call this 9, call this 10. Doesn't have to be very strict. Okay, you can number anything you want. Okay, but I do it like that, left to right. Okay, what's the significance of the numbers? Okay, what numbers are we going to pay attention to? Exactly. Okay, guys, you'll see, I only want to pay attention to 2, 4, 5, 7 because these are the carbons that are involved in the combining. But first of all, guys, carbon 2 is attached to what? Okay, try to just visualize now. Okay, you want to attach it to 2, a 2 you can attach to 5, you can attach to 7, doesn't matter. Okay, here they never say is go what restriction. Can you see that? Okay, so what I'm going to do is this. I'm going to take 2 and attach it to 5. Okay, then. Imagine I turn this around, then I plug it there. Okay, I flip around, plug it. Okay, you want to turn it one more time, you can now. Okay, but basically, can you all see 2 must combine with 5, and 4 must combine with. Okay, that's more than matters. Okay, what I'm going to do first, since this guy is bigger, let me just draw it first. Then I lift it and place it on top. So I'm just going to draw the same thing as what you see up here. I'm not changing anything. Okay, but in fact, I'm just going to write down 5 and 7. These are the 2 important facts. So if this is 5, then this is 1. 2 long. If this is 7, this is 4. Okay, in between 2 and 4, what do you have? 3 long. Then just add it in. 2, 3, 4.
Ah, so you like, oh.
Yeah, I flip this around and just keep it on top. Okay, we are not done yet. Yeah, that's 1. 1 is bonded to 1.
2. Oh.
1 is 2 is 3 is 4, 5, 6, 7, 8, 9, 10, all done. That's it. Now, you want to put, okay, some of you guys say 2 bond to 7, 4 bond to 5 is 10 as well. Yeah, the 1 will end up sticking here instead. But it doesn't matter. I know it's a different structure, but we will still accept for this question. Okay. Yeah, I think we need to do one more question first. This one too fast. Yeah, okay, before I take a break. Yeah, okay. But those are done. Turn over to level up question 1. We're going to go into the quick man territory. Quick movement. Don't worry, don't worry. I'm just gonna. We're not gonna do the whole thing yet. Okay, any more questions for this part? Okay, this one I suggest you guys are going to try it again because this one show you all how it's done. See whether you can do the same thing again. It will be more rewarding in that sense. Okay. Yes. Oh dear. Finish your A-levels today.
I know, right? Yay.
The bio kids. Bio kids sad. You don't know. Okay, any questions? Okay, go on. Okay, come, let's go over to level up question 1. Start to get a little bit tougher already. I'm more focused on the pattern recognition part. What I want you guys to do, just read that first page. What page is it? 10. Okay, go to page 10. Just read page 10. Page 10 has part A only. That's what we're going to do here. Yeah, see whether you all can do this. Okay, they give you a lot of nonsense. I'll just read first. That's for part A. Basically, these 2 guys gonna take part in the reading reaction.
Oh, okay. Oh. Oh no. Not so home.
Try read first. Slowly, I'll go and try to decipher. Wait for carbon to come back. Panic. Wait for carbon to come back first. Okay, what part do you want to understand here? Okay, so I know it's a little bit confusing, but let's break it down. Okay, the title of this question is called pattern recognition. Because what's happening here is they taught you guys this thing called a Wittig reaction. We don't even learn the Wittig reaction. No, we never learned that shit. You're not supposed to know, right? Okay, so we have never seen this thing. But now they are teaching us, right, how a Wittig reaction looks like. It looks like this. It's just this. Okay, so they want you to basically draw the products of something that also undergoes a Wittig reaction. Okay, so they give you these two in part A, and they want you to draw the products. So what we're going to do here is this. I don't know how the Wittig reaction works. No one does. So that means this kind of question here is called pattern recognition. Every time they give you a weird scientist name, you call that pattern recognition. Because all you can do is to see a pattern and copy that pattern onto your answer. That's all you can do. You don't know how this thing works. So first things first, the most important thing about pattern recognition is that the equation that they give you is basically the one you need to refer to. Okay, you must study the equation. Let's phrase it this way. Okay, please study the equation and try to study a pattern that comes out from it. Okay, maybe it's not so a pattern, but sometimes you want to list out, right? Okay, as many observations as possible. Okay, and then afterwards, right? Okay, after you list out whatever observations, just apply those observations into your answer. So you're just learning something new on the spot, basically. Okay, this is what they give you. So you're trying to learn something new and then apply that knowledge here. Okay, of course, most other questions, organic questions, you already learned things, so they're testing you. But here, right, is something new. Okay, guys, so what I want you to do now is this. The Wittig reaction, you must try to study it as hard as possible. I want you to look at the before and the after. What do you notice? Anything that comes out. What do you see? Just tell me. Okay, the CL is gone. Okay, that's number one. Okay, so I'm just gonna circle the CL. CL is gone. Okay, anything else? Before versus after. Before versus after. Keep comparing. Oxygen is gone. Okay, so O and Cl are gone. Then what happens afterwards? Anything else? Okay, one less H over at here. Okay, so they take away one H, then become CH2 then. Okay, form between. Basically, both of them combine together. So this is what's happening. I'll summarize again. O, Cl, and one H gone. And then they combine together. Okay, so you can write these two things out first. Okay, eventually, when you all get good at this, don't need to write. Okay, number one, O, Cl, 1H gone. And then just combine. It doesn't have to be legit. This one just going to write down something that you understand yourself can read. Okay, that one not marked. Okay, but let's try to interpret a bit. Okay, when you all remove the O and Cl, how come still need to remove 1H? Why do you need to remove that 1H? Okay, can't you just combine these two guys together with a double bond? Why can't CH3 form a double bond with this C? Yeah, C cannot have 5 bonds, right? Yeah, that's why they remove the H. So even though we are learning a completely unknown reaction, right? Some things still need to make sense. Like this. Okay, repeat the same thing for this one. Okay, you see the products, are they very different from what is given? Not at all. So let's try to draw the products for this. Okay, again, what happens? O is gone. Okay, sometimes circle out, it's easier to see. The Cl is gone, and what else? 1H. Okay, the H from where? There's so many H's. This one? Now remember, why do we remove that 1H? So that you don't form 5 bonds, so that this carbon can form a double bond with this guy. So if you remove the 1H from CH2, and it doesn't make sense, right? You're combining at this carbon here after you remove the Cl, right? So that's why to form a double bond here, you remove the 1H from this guy. Okay, can see that? Yeah. Okay, let's try to draw the products. Okay. Never mind, you just draw one first. Draw one. Okay, you will see why there's sequence isomers.
No, more money. Okay, can I go to Ireland? I thought
Okay, so you all notice why you remove the H from here. So it becomes CH, then CH3. Then CH, CH3, 4 bonds. Okay. Do you notice? Can this guy undergo cis trans isomerism? Yes. The one that I just drew here is what? This is cis. And trans just go and stop the one on the left.
oh, we have to do that.
Okay, go and find two common groups of both carbons. In this case, the CH3 are the common groups, same side versus opposite side. Okay. Okay, so this is an introduction to pattern questions or pattern recognition. Okay, so expect more to come. Okay, with that, can you all try part B?
B.
Okay, what do they want here? What are we supposed to do here for part B? Okay, compared to a Wittig reaction that we learned just now, this guy came from a Wittig reaction. So they want us to draw the reactant. So this part here is about working backwards. Refer to the reaction here that we learned. And this is what we list out just now. You combine the double bonds and then you remove all these things. So now you just need to reverse those two steps. Instead of combining, you separate the double bond. Start with that. Then you do whatever to add back the O or whatever. Give it a try. Okay. Yeah, why got one ring come out? What's going on here? Right? You find this. Guys, it doesn't matter whether there's a ring, there's 5 rings. Doesn't matter. Just reverse the 2 steps. They give you whatever nonsense, you just need to stick to your principles. Cannot. Okay, one time. Go take a pencil, start literally go and like cut the bond. Okay, cut first, then draw what it looks like after you cut. Okay. Like perhaps if you cut already, there's a gap in between here. Okay, go and cut. Take a pencil and start experimenting. Okay, this kind of thing must try.
We could add in the
I didn't know you're adding the C. That's not part of what we discussed. You're just removing the 1 H from the C. So now that means that 1 carbon must add back that H in reverse. You see, If you want to reverse the process, I can cut these two guys. Okay. So you can, okay, let's say you're struggling with the pattern here. Doesn't matter. You'll go back to the easier question here. Basically, the equation again. And you try to work backwards yourself. Okay, you experiment with something easier first. So this is level 1, then now you're trying level 5. Now a bit difficult. Okay, let's try this now. Okay. Okay, let's try to cut. We cut the double bond first. So when you cut the double bond, I will now have this part. Okay, and this part. Right? Okay, but this double bond here eventually becomes a single bond, right? Because you need add back one H. And then at the same time, add back one Cl. So you see, the Cl that H is added back on the same carbon. Okay, so here, by you add two things, you need to remove the double bond. So CH3, Cl. Okay, so I've got one structure already. That means the other side, with the double bond, you're only adding one thing, which is hold. You try the same thing, you rehearse once, then you try the real thing. Okay. Okay, so I suggest what I'm doing here is I am just experimenting with something easier. This is way easier because this is where we learn the rate reaction from. Okay, so perhaps if you reverse the reaction here, what you all can try first, separate the double bond. So it looks like this. Okay, draw it bigger. And again, you can see what I'm doing here, just draw it bigger. Okay, I have separated the double bond. Okay, you can see I just take a scissors and cut. Yeah, I don't do anything else. I just leave a gap in between. Then slowly make the modifications. Okay, one side your double bond O, the other side your single bond Cl. In modify. Okay, draw a squiggly line here to show where its bonds are getting cut. You can label the carbons if you want. Call them A, call them B, call them whatever. Right?
How do you keep the double bond?
I don't modify it. Simple. Okay, you see, right, you cut already, only one side already the double bond. Okay, so you that right now I just cut, I don't do anything else yet. Yeah, okay, so I don't modify that. Yeah, okay, you need to add back the Cl. Oh, just now I take away, but then now I need to add back. Split into two things. Okay, we'll get to that. But no need. We'll get to that. Okay, guys, a few questions come out already. Those I need to address. Okay, can you look at this? Okay, I first cut the double bond, separate it first, because that's what I need to do here. I'm just following what I learned just now. Cut the double bond so I get this. You can draw this as a blueprint. Don't expect yourself to draw the final answer straight away. No. Okay, you can't do that yet. Draw a blueprint, and then look up. I've covered A and B. Use whatever tools to help you guys. Okay, so I've covered A and B equivalent here. Yeah, do O first. O very easy. Go and find the double bond. I just put for B. Okay, just add back the O. Okay, done. Okay, that's my left. But the right hand side is a bit more tricky because I need to remove the double bond. And then I need to put back the H and the Cl on carbon. Okay, I can put back the Cl, I can put back the H, but it's invisible. Okay. Now the next thing is this. Some of you guys are asking me, do I have to split this to two compounds? Because it started off with two compounds. Answer is no. Because I need you all to look at this. Okay, I mentioned this just now because next time when you all see a ring being formed, a ring being formed means the reaction happens how? How's the reaction proceeding here? Is it between two different molecules? It's within the same molecule, right? So this is also known as a one reaction. Yes. Okay, take note, guys. Intramolecular reactions will form rings. And, right, there will just be one reactant. Make sense? You need one reactant only, but the reactant just reacts with itself. So one is enough. You don't need two. Very common one, okay, they very commonly give you guys 2 first. Okay, but then eventually, right, they give you a ring structure. If a ring structure is formed, I say again, that means there's an intramolecular reaction, meaning only one reactant. This one reactant here. Okay, but is this the only answer? No. Okay, because if you all realize just now, right, let me just draw another alternative answer. Okay, I just now cut a double bond, so it looks like that, right? Right? Okay, so y'all see this? Oh, it's gone. Okay, y'all see this? Okay, I got my carbon A and B again. He saw the chemistry and he just like, it's like, yeah, okay, but okay, that's A. Okay, then he was like, okay, see first, just now I put the double bond on O on D, right? But I can add the double bond O on B also. That means A, you must remove the double bond and just turn this guy back to HCl. You can do this also, another possible answer. Okay, you have to stretch this out now because you all notice this is a straight chain. You stretch this out, but go down. Very hard to visualize. So just suggest start from the ring and end up with the structure. Okay. Yeah, they are isomers. Okay, there are 2 different compounds. Okay, all good. Yeah. Suggest again, go and try this for your own time. Right? Okay, I think we go through part C and we take a break. Okay, part D and E is mechanism drawing again. Okay, we go through part C, okay, to wrap this up. Right, you'll read the question, okay, we discuss together. Yeah, I already did it. Okay, yes. The only thing different thing that is there. Yeah, just I bother to see. Just means there's a single bond in between. Yeah. I know some of you are going overseas, right?
Okay. I can't Really? Friday, right?
Yeah.
Yeah, I can't come next week. I have
Okay,
come.
no, you don't. You haven't graduated.
Yeah. You're going? Yeah, but I just feel very funny in my case because it's full black, long, no slit, no revealing parts. You know how the funny part is?
Just wear a jump. Cover everything and go there. Hello. Assalamualaikum. Well, I say all this on recording one day, right? You're gonna dig this. I'm gonna get cancelled. I swear to God. All my criminal activities all from there. What? Okay, we'll discuss that question. Okay, but I think next week, okay, because we need complete lessons but we have 2 more weeks. And that's before okay, some of you guys flying before that, I understand. Okay, then I'll just send you guys recording. But 2 more weeks before I also prove. Okay, so we have 3 more lessons to complete the next 2 weeks, possible. Yeah. Okay, so next week we might do 2, might do 1. See how.
Yeah, but next Friday.
Okay, never mind. Then I'll probably send recording. But another one will be scheduled later. Okay, guys, come. Look at ICL. Okay, ICL versus normal S halogens. The difference is the polarity. Okay, why are we talking about polarity here? Because reacts with alkenes faster. That's the keyword. Reacting faster. Now remember, how do the halogens react with alkenes? You just take a normal S alkene here. You take a halogen. Then it's just a rich attacking the poor, right? Something like this. But versus, if you just take, let's say, ICL, same thing, rich attacking the poor. Let me just show 2 arrows, faster. Somehow this is faster. Why? Okay, don't ever draw two arrows. I'm just showing you guys the difference. Why is this faster? Okay, we talk about polarities. Okay, tell me what do you notice about polarities? Okay. In fact, is there even an electronegativity difference here? Okay, so that means for X2, they are what? Non-polar, whereas ICL is. Okay, remember guys. Sure, polar, you're gonna have a partial automatic. This one, is it automatically there? How did this come about? Here we have. Okay, you put it close enough, then it came about on the spot, right? It's induced, it's created on the spot. Which one better? Okay, of course, the one that's been here forever, right? This also is a what dipole? This is an induced dipole. This is a permanent dipole. Permanent dipoles are so-called stronger. Okay, so you attack faster. Okay, so let me just write this down. Okay, first point, you tell me X2 is non-polar, ICL is polar, number one. And because you're non-polar, you have an induced dipole. Whereas for polar, you have this thing called permanent dipole. Then we wrap things up, we answer the question. Because it's a permanent dipole. Okay, can you all tell me so that this guy is a stronger one? ICL stronger is poor, is getting attacked. What do you call something that's poor? Electron division, okay, electro. Yeah, okay. So ICL is a stronger electrophile. And will react with alkenes faster. Again, this is 1 mark, so that's why we don't go too much into detail. After writing all this, highlight the keywords. Okay, permanent dipole definitely better than induced dipole, so it makes it a stronger nucleophile. That's okay, 1 mark. Oh, good. Yeah. Okay, we take a break first. Okay, until like 8:40, right? Then we later try more.
Yeah.
Okay, level up question 3. Stick man, no lah. They just give you a bunch of compounds. Okay, and then you just need to answer the questions. Okay, like try part 1 first. Reagents and conditions. Okay, once done, try part 2 also. Okay, part 1 and part 2. Yes, correct. Okay, part 1 and part 2. Every time Carmen does chemistry, all the negative thoughts start to come in. I hate my life. I feel counsel. We must need people.
I think I need. Why is there one? Oh my god, the two of them are too expensive. Oh, you're not like. I think she wants to see your mom just takes the name, she's like, no.
In not trying to do part two, never mind. I'm going to at least try formulate some answer. Then I think part three is also one mechanism. I'm going to try the mechanism. In part four, then we will do together separately. Okay, 1, 2, and 3. Yeah. We can. We'll show you an answer for part 1. Okay, 2 more minutes. Okay, some answers on the board. I'm mostly going to discuss part 2. Okay, come, let's go through. Okay, for part 1, same exact answer as before. The difference between limonene and this is the terminal alkene. But okay, same answer. Okay, then this one I don't write. All good. Okay, for part 3, mechanism, go and check tertiary carbocation, not secondary. You put the positive charge on the tertiary carbon, but the other carbon check that you have your BR. Okay, this is usually where the mistake lies. Don't forget the BR. Okay, then afterwards you just attack as per normal. Again, I'm not going to attack the plus charge. Okay, so I put it on opposite sides, so it's very clear. Okay? Okay, let's look at part 2. Okay, for part 2, I think you all have kind of discussed the answer already, right? Okay, menthone is basically an alkene. Then methane, mentane, or whatever, right, is just an alkene. Why is it that alkene can react with HCl, but alkane cannot? That's what they're trying to say here. Okay, so you all mentioned that it's something about reactivity. No, sorry, you all mentioned something about unsaturated or saturated, right? I wouldn't say it's wrong, okay, but then there's a better way of looking at reactivity as a whole. Okay, reactivity, we are looking at rich attacking pore. Okay, write that down first. Okay, for reactivity, if they mention the word reactivity in the question, like the word reactive or unreactive, you must discuss anything to do with rich and poor. Now, if you look at the overarching functional group, alkenes can react with HCl. You have never seen alkane reacting with HCl before. Why is that so? Guys, take a look at HCl. Why is it that alkenes can react with HCl? Follow this framework. Alkenes, okay, alkenes are electron rich, and HCl is an electron poor region, right?
Yeah.
So that's why they can attack lah. Okay, but you try the same thing for alkanes. Does it fulfill this criteria? Okay, alkanes, is there any rich region? Is there any poor region? Yes, neither. Okay, that's one of the reasons why alkanes are very unreactive compounds. There's barely any reactions that we learned in the topic, right? Because of the fact that it doesn't have any rich or poor part. That's why there's barely anything you can understand. Okay, so same idea over here. Next time when the question talks about, okay, next time when you talk about reactivity, talk about rich attacking poor, whether this is possible or not. Okay, so don't just mention unsaturated and saturated. Okay, so alkenes first tell me that, okay, alkenes. Now don't just tell me that double bond is rich. Tell me this, alkenes have a high electron cloud, which is electron rich. Okay, so it specifies this. Okay, and hence can attack electron poor regions. Okay, like HCl. Okay, compare that, contrast that with alkenes. Okay, how many marks is this? 1 mark? Okay, yeah, whatever. Okay, so alkanes do not have any electron rich or electron poor region. Okay, so it don't have any rich or poor region, so it just can't attack it. Right? Just say that dust is unreactive. Okay, so highlight the keywords again. Okay, high electron cloud is rich, that's why I can attack electron poor regions. Alkanes do not have any, okay, that's why it's unreactive. Okay, we're going to discuss part 4. Okay, before I move on to the last thing for today. Actually, wait, let's move on to the last part first. Okay, after you're done with this, turn over to question 6.
Wait, the last one.
I don't think we have time for that. Yeah, read question 6. Okay, read through that first, we'll discuss together. Yes, it is 8 marks. Yes. Okay, so once everyone's done, we'll discuss this kind of question. Okay, but elucidation is basically detective work lah. They give you clues, and your job is to find the structure, the exact structure. Can be done. Can be done. It's one of the most daunting type of questions we will see. That's why we need to start now. Okay. Read through first, alright? Okay, so elucidation, they'll give you unknown structures. They'll give you clues until you can get the exact structure. Sounds a bit impossible, okay, but it can be done. Okay, that does sound like hell, okay, but then it's actually not that bad. Because I can tell you guys this first, we'll write down the format of getting marks here. The 8 marks are not just like the whack up. Okay. There are 2 things for you guys to fulfill in a structural elucidation question. First one is deductions. Now guys, think note, this is where you can get as much marks as possible. In the actual exam, this type of question, the second part, very difficult to get structures. The deductions are where you can build the most marks. So you must know if you study well enough, right, your deductions can get up. Okay, because you're like solving detective work. They give you a reaction. Then you just tell me what that reaction, what that reagent and condition is, something like that. The structure is the one that's difficult for obvious reasons. Okay, so guys, let's look at deductions out. To get 1 deduction mark, you need to fulfill 2 things. Number 1, you need to tell me what the type of reaction is. Is it addition, elimination, oxidation? Just give me those. But after that, you must then tell me what functional group is present. Of course, because our functional groups are like the most important thing for us to get structure. So once you fulfill these 2 criteria, you can get 1 deduction mark. Usually, guys, how many deduction marks is half of the total mark? Okay, so 8 mark question, 4 marks for deductions, probably 4 marks for structures. Okay, so something like that. Usually structure 1 per mark. But here we only have 2 structures, A and B. So 2 marks. Okay, usually there's a lot more structures now. Okay, so we shall see. I'm more focused on the deduction segment. The structures we'll do together. Okay, so again, I want you guys to start presenting your answers this way. Your deductions come from the question. So the question is basically, the question is giving you clues. And your job is to deduce those clues. Okay, so first of all, guys, let's read the question together. 2 compounds A and B have the formula C6H10. Again, now C6H10 can be anything. So that's how we're supposed to figure this out. Okay, both decolorized bromine is CCl4. Pause that. Okay, so go write this down. Okay, we start here. Okay. A and B both, okay, don't write word for word, because that's stupid, right? Okay, you're wasting time. Okay, so write in broken English because it doesn't matter. You'll not get marks for this or penalized for this. A and B are both C4H10, both decolorized Br2 in CCl4. What on earth does this mean? Okay, what does it mean if you can decolorize Br2 in CCl4? Okay, let's fulfill this. What type of reaction is this first? Okay, urea Br2 is CCl4, electrophilic addition. What functional group is present in A and B? Okay, good. A and B have alkene. That's point number one. Okay, later after we're done that, I will copy. Okay, we just continue. Okay, next. A and B yield the product C6H12. Okay, both are the same. When treated with excess hydrogen in the presence of catalyst. Okay, let's shorten that first. A and B, okay, I'm going to shorten it without any words. A and B are both C6H10. Then they react with H2 in a nickel catalyst to give C6H12. See how fast this is? Okay, this is your summary skills. Okay, you can use arrows now. Okay. Okay, what reaction is this? Okay, you want to find addition or reduction, both are fine, but prefer if you guys use reduction. Okay. Functional group. Okay, alkene, but sounds like a waste of time, right? Already had that just now. But there's something more specific in this reaction. Oh, we know that. Okay, so H2 is nickel catalyst reacts with an alkene. Okay, so A and B and alkene. We already established that just now. But you notice, just now it's just a reaction. Now they tell us the molecular formula. What happened from before and after? Plus 2 hydrogen. And that happens, right? Whenever you take alkene and then you add a hydrogen, become alkane, right?
Yeah.
Okay, so how many alkenes are there? Okay, in A or B, just one of them. Because they are the same thing. Okay. They each have how many alkenes? If they only turn from C6H10 to C6H12, just one. If it's 2 left, what will it have turned into? 14. Good. Yeah. Okay. See the idea here. The number of H's that you had, okay, will tell you how many alkenes it has. That's why the molecular formula is very important. So because of this information, you can tell me A and B only have one alkene each. See what we're doing here, right? So they give you molecular formula not for fun, right? They have two. Okay, next. Okay, I'm just gonna write there. Okay, so next paragraph, oxidation of A. Now we talk about oxidation. With hot acidified KMNO4, you all know what that is. Gives you, okay, highlight only one organic product and carbon dioxide. Okay, we write that first up. A, and you'll notice I like to do this. I love to write the molecular formula every single time. I don't care if I wrote it there just now. I'm going to write it again. Okay, very good for reference. Okay, next time you see why. I'll just do that now. Okay, A with KMNO4, some acid, a bit of heat. Okay, will give only one product plus some carbon dioxide. Okay, let's just answer the questions. What reaction is this? Okay, good. Oxidative cleavage. All right. Second. What functional group? Okay, now you can just tell me alkenes again, right? Okay, but that's kind of a waste of time, right? Okay. Good. Okay, you have to add a bit more value here. There could be a terminal alkene because of carbon dioxide. Good. So write it down. Yeah. Here, A has terminal alkene. Okay, but guys, they never specify how many carbon dioxide there are. Okay, is there another way to produce alkenes? Sorry, is there another way to produce carbon dioxide without terminal alkenes? Okay, that one, right? Okay, or how do we mention that? Okay, or ethane dioic acid produced. Yes, okay, so the alternating double single double bonds. Okay, you could either have ethane dioic acid or terminal alkene. Meaning to say, you could see a double bond at the end somewhere, or you could see the double single double pattern inside. We don't know yet. Okay. Okay, yeah, no, it's two separate things. Terminal alkene could produce carbon dioxide. Ethane dioic acid could also produce carbon dioxide. Okay, I mentioned these two, but actually only one of them is correct. Which one is wrong? Definitely out over here. Yeah, this one. Why is this wrong? Let's backtrack a bit. What have we discovered just now? Okay, to produce this ethane dioic acid, what's the pattern again? Double, single, double. There needs to be at least, exactly. You need at least two double bonds. But really established there's only one. If there were two double bonds, what would have happened here again? Okay, so we just erase this. Okay, don't erase, put a line through it. Don't question it, because I want you to acknowledge it. This is still technically possible, but we cancel this out here. And I want you to note why. Okay, you all understand now, but we'll forget in a day. Okay, so ethane dioic acid. Let's go note, not possible here. Okay, take note, guys. You don't need to justify this. Okay, you do not need to justify this to your examiner. Just remove it in the exam. Okay, don't need to justify, but I want you to write here. Not possible here as, sorry. Oh, only one product and then carbon dioxide. I'm just trying to shorten the thing. Okay, not possible here as A only has one alkene. Okay, then you just write this requires two alkenes. Something like that. Okay, again, don't need to justify this next time. Next. Okay, last one. Similar treatment of B, so the exact same. B is also C6H10. You undergo this KMNO4, H2SO4, and E. And guys, they actually give you the product here. Okay, let's draw out this product. Okay, HO2C, 4 carbons, 1, 2, 3, 4, and CO2H. Okay, let's do the reductions. Okay, same thing. Reaction type here is just your oxidative cleavage because they say same treatment. But let's come out with a reduction. Okay, so you all notice when I say the reduction of functional group, it's not as simple as just O helps. Okay, there's a bit more value to it sometimes. We know B as alkene, obviously. But there's another very important idea. And the clue is, guys. Okay, everyone on the same page. Look at this one. B, okay, if you undergo oxidative cleavage, what will happen? Usually you will get how many products? Multiple, right? Doesn't have to be two, right? What do you notice here? Okay, why is there only one product? That's good. Okay, usually oxidative cleavage should give you at least just a breaking things. But after you break already, right? Still not one product. Why? How come you break something? Okay, no matter how long, how weird looking it is, you cut another one, you're gonna break it. Exactly. Guys, B is a cyclic structure. Because only cyclic structures you break already, you still get one product. You can see that. Okay, there's no intramolecular reaction here. Okay, so let's not write that. You must write this down, okay? This one suggestion I have. Another way you all can do this is how many carbons are there in the product?
6.
Okay, 6 carbons. You initially had 6 carbons. How come you cut already never reduce carbons? It's because it's cyclic. Okay, you can write something like no change in carbon atoms, in number of carbons, which means B is cyclic. Again, don't need to be in perfect English. And usually after you do this, you won't have time to do your structures for now. Okay, then usually after this, you can just move on to the next question. Okay, but we need to get two structures here. Okay, let's just get that. Okay, which one should we try drawing first? Okay, B lah. We know B is cyclic and 6 carbons. 6 carbon cyclic, what shape? Okay, just draw that. And anything else to add in? Okay, you look through your deductions, BN was a double bond, right? Place it somewhere. So that's the answer for B. But guys, every time you draw a structure, I want you to check something. Check what? Check with the molecular formula. C6H10. Okay, 6, obviously there's 6 carbons. Are there 10 hydrogens there? Okay, just go and always check out 10 hydrogens. Okay, yes, good. Okay, so done. That's B. Okay, somehow we need that A. Okay, but everyone okay so far?
Wait,
Okay, B cyclic. 6 cyclic. A. How do you get A? Okay, check through your list. Okay, A as alkene, no shit. A only is one alkene. Okay, we bear that in mind. It's a terminal alkene. Okay. So terminal alkene, just put a double bond at the end. Okay, but how do we draw the 6 first? That's all we know for A. But 6 carbons got so many permutations. But remember, okay, we need to look out for these two things. You have only one organic product from this. The other one is carbon dioxide. Okay, let's just draw 6 carbons in a straight line. You in doubt, just draw straight chain first. Okay, 1, 2, 3, 4, 5, 6. What else do you need to add in? Where? Yeah, like N. Okay, so you cut this, you get carbon dioxide here. Good. Perfect. Okay, my organic product and carbon dioxide. Anything wrong with this? Doesn't seem like anything is wrong, but just now I say you must check what? Check your hydrogen, check your molecular formula. So check this. Is this C6H10? This C6H1. Oh, what? Okay, this one is C6H. Oh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Then 12 here. Okay. I think this or something. Hey, how about C6H12? But I want C6H10. Usually, what you do to reduce RT? Another double bond, but I can't add another double bond. So how? Cyclic again. Okay, remember what I said the other time? Alkenes. Okay, wait. Alkenes is what's the general formula for alkenes? There's something else. There's this also. Cycloalkanes. Meaning to say, guys, cycloalkanes are okay. You want to reduce hydrogens, right? You don't need to just add double bonds. Turning into a cyclic structure already makes it safe. Already reduces the hydrogens as well. That's it. Oh yeah, it's terminal, but it has to be cyclic. But you see, cyclic, can it be terminal? But right now, can any of the double bonds be terminal? Yes, exactly. I say again, there is a terminal alkene and the hanging around at the end, but yet there's a cycle. So how does that look like? Oh, what's that? How big is the ring? How big is the ring? Yeah, because we need 1 for put it here anywhere. Where's the double bond? Must be the end hanging out here. What's that jelly? So it can be 4 cycle. Guys, it can be 4 as well. 1, 2, 3. Because it never restricted us. Square, then how? What's next? You want to put like that before a double bond here also can. You want to put like that also can. There's so many possibilities. Okay, but just stick to this. I'll go and draw the square. Screw that. Okay, my point here is this. There's terminal alkene. Okay, I say it here. I know it's quite confusing. There's terminal alkene. There should only be 1 alkene. But just now we did 1 alkene doesn't fulfill C6H10. Okay, that's why you draw another ring. Okay, ring will also contribute to less hydrogens. Okay, so this question a bit tough. Okay, but good introduction to investigation. Again, that's why I say structures are hard to get. You probably spend too much time. Just move on to the exam. Deductions. Once you get these out, do it. Okay, that's it for today. Okay, I know we had a bit.